Hello everyone, I am Eslam Hafez. Today I will make a presentation under title Multicolor Diagnosis of Salivary Alkaline Phosphatase Triggered by Silver Coating Gold Nano Pyramids. Our target is detection alkaline phosphatase ALP, and ALP is an enzyme able to catalyze proteins, nucleic acids, and some small molecules dephosphorylation. It'll be found in many fluids inside the body, and one of these fluids is saliva. And salivary ALB is used as diagnostic tool in medicine and industry. And this is the comparison between healthy people and between BD. BD, means that periodontitis. And periodontitis, this means that inflammation of the tissue around the teeth, often causing shrinkage of the gum and losing the teeth. And this is the comparison of the concentration of ALB inside the saliva between healthy people and between BD people. And also, salivary ALB is one of the sensitive markers for early detection of oral carcinoma. This is a graphical abstract detection of ALP by glucose. First, we collect saliva, whole saliva or from fluid from GCF, and then these fluids contain ALP, and we add glucose phosphate as substrate for ALP. ALP's enzyme will make dephosphorylation of this glucose phosphate to convert it to glucose, and then glucose is reducing agent, so it will make reduction of silver ion on the surface of the gold bipyramid to give you looks like this shape. And was increasing the concentration of ALB, it give more glucose, it will make more reduction of silver ion around the gold nanobipyramid to give you more thickness of the silver shell around gold nanobipyramid. And because of LSPR phenomena of the gold, this make shift in wavelengths, absorption wavelengths, and this make multicolor detection from reddish brown until red, passing through green, blue, and then purple. First, we prepared gold bipyramid by using a seed-mediated growth method. In this method, we prepare seed first, and then we inject the seed in growth solution to get gold bipyramid. But in this method, we got gold bipyramid and other shapes, looks like spherical, and this is the UV spectra for this solution, and this is the absorption spectra characteristic for gold bipyramid, and this is for spherical. So this is mixed solution between bipyramid and spherical gold bipyramid. So we have to make purification, and this purification to get monodispersed gold bipyramid. So we made precipitation of silver around gold bipyramid to make nanoroots, and these nanoroots consists of gold bipyramid and silver nanoparticle around gold bipyramid. This by using vitamin C as reducing agent and CTAG as surfactant. And these shapes will precipitated on the bottom of the beaker, and we collect these. Second step, we collect these shapes and then make etching of the silver around the gold nanobipyramid to get gold nanobipyramid only. This by using H22 in basic medium. And this is the characteristic UV for gold nanobipyramid. It is the absorption band around 740. And then we make optimization of glucose detection by reduction of silver on the surface of the gold bipyramid. So we make optimization for three factors. First one is pH, concentration of silver ion, and concentrations or types of CTAB. First, the pH. All of us know that glucose is reducing agent, but it's not working unless in basic medium. So we change the pH to higher from 8 to 13 to get the optimum pH. With increasing the pH, the shift in wavelengths increase until reach to 11. After that, the shift decrease. So the optimum pH that we found is 11, and this is because of when increasing the pH, the ability of glucose as reducing agent increase until reach here. After increasing this, there is precipitation of silver ion as AgOH. And second, Second factor is concentration of Ag ion, silver ion. We found that 10 is the maximum, is the optimum concentration of the silver ion. And also we found we mixing between two surfactants CTAB and tween 20, and we found that the ratio between CTAB to tween 20 is 2 to 0.25 millimole. And this is glucose detection by reduction of silver on the surface of the gold nanobipyramid. So with increasing the concentration of glucose from 0 micromole to reach to 70 micromole, there is a shift in wavelengths, shift in absorption wavelengths from 740 for 0 until reach to 560 for 70 micromole. And this is the relationship between shifting in wavelengths and concentration of glucose. We get this relationship from 0 until reach to 70, and this is the linear range between shifting in wavelengths and concentration of glucose. The linear range is around 0.1 from 1 micromole to 25 micromole. And this is the change in the color between when changing the concentration of glucose, it's changing the color of the gold nanopyramid from blank color until reach to red with changing the concentration of glucose. This is TEM images for different precipitation of silver on the surface of the gold nanoparticle. First image we found gold nanopyramid only without any silver shells, so the color is brownish red. And we found thickness of the silver around the gold nanopyramid, so give us green, and with increase this shell more and more will give us red. And this is EDS analysis for gold nanopyramid and the shell of the silver around it, and we found that the outer shell is from silver and the inner shell is in gold. This is the optimization of ALB detection by reduction of silver on the surface of gold nanoparticles. So there are two items. The first one is glucose phosphate, second one is an incubation time between ALB and between glucose phosphate. So to get the optimum concentration of glucose phosphate, we tried different concentration of glucose phosphate with different concentration of ALB, and we found that with increasing the concentration of glucose phosphate, the shift in wavelengths increased with all concentration of ALB until reached 1.5. So 1.5 is the optimum concentration of glucose phosphate. 1.5 millimole is the optimal concentration of glucose phosphate for this experiment. And also in incubation time, we made the same different times with different concentration of ALB. We found that with increasing the time, the shift in wavelengths increase until reach to 45 minutes. So this is the optimum time for this experiment. This is the UV spectra for detection ALB. We increase the concentration of ALB from 0 unit per liter until reach to 50 unit per liter, and there are a shift in wavelengths from 740 until reach to 560. This is 180 nanometer shift. So here we draw the shift in wavelengths against concentration of ALB, and this is a plot for it, and this is a linear relationship between shift in wavelengths and concentration of ALB, and we found that the linear relationship between 0.1 unit per liter until reach to 20, and the LOD for our experiment reached to 0.085 unit per liter. And this is change in color from blank 0 unit per liter until reach to 50, and this is the change in the color of our experiment. We made selectivity and interference. So we choose for selectivity, we choose the most common biomolecules that found in saliva and make comparison between them and between ALB. And we found that ALB only make shift in wavelengths comparing to all the other biomolecule in saliva, and this is the image for it. And also we make interference between these biomolecules and between ALB, and we found that there is no big interference between between this biomolecule and ALB. And this slide for detection ALB in saliva, this is a real sample. So we collect saliva from 3 volunteers, volunteer 1, 2, 3, and then detect the concentration of ALB in this saliva by standard addition method for our system, and calculated the concentration of ALB in these volunteer salivas, and we pursue the standard kit and make comparison between the result from our system and the result from standard kit, and we found that almost the same. Also, we made recovery rate percent for the sensor by collecting saliva from volunteer and calculate the concentration of the ALB inside it by standard addition method. It was 46.7, and then adding a standard concentration of ALB to it, standard concentration 5, 30, 50, and then detecting the concentration of it by using standard addition method and calculate the recovery rate for it, and our recovery rate is around 98.5 unit per liter. And this is our conclusion. We successfully developed a multicolor biosensor for ALB assay based on modification of both composition and morphology of gold nanobipyramid. The bioassay is based on the selective catalytic activity of the ALB to dephosphorylate glucose phosphate substrate into glucose, and this makes reducing silver ions into silver nanoshell on the surface of gold nanobipyramid, and the controlled growth of silver leads to color change as a function of ALB concentration, and finally the spectral changes exhibit a high sensitivity to ALB detection, enabling us achieving the low limit of the detection, 0.085 unit per liter. Thank you for your listening.